So welcome back. This video is going to talk about a lot of the decisions that you'll have to make whenever you do a cluster analysis. So the first step is to either write your questionnaire or create feature variables from different relational databases. I think of this as preparing your palette. So creating a cluster solution is kind of like making a painting, and before you can make that painting, you have to squeeze different colors onto your palette before you can start doing the painting. Now, I really like this analogy because if you think about painting, and let's say I squirted a lot of green and yellow paint out on my palette and I used green and yellow, you know what? The painting's going to turn out to be a lot of green and yellow. Alternatively, if I had used red and blue, then my painting would turn out to be red and blue. So which one is right, green and yellow or red and blue? And the answer is, it really depends on what you're trying to achieve. And the exact same thing is true when you do clustering. So if you use certain variables, if you use a lot of behavioral measures, you're going to have clusters that are primarily defined by behaviors. If you use a lot of attitudinal and affective measures, your clusters will get defined on affect. Which one is right? Well, it depends on what you're trying to achieve. The second step is to consider initial splits. Initial splits are where you have identifiable groups in the data that you would never want in the same cluster. So one example of an initial split could be B2B versus B2C. So if I'm a company and I sell stuff and some of my customers are other businesses and other customers are normal consumers, I may want to just separate that out because perhaps I'd never want to have businesses which have very distinct needs. They have different billing systems, different payment systems, and consumers in the same cluster. So consumers want to pay with their credit card or maybe a check, whereas businesses have very different approaches. Let me give another example of an initial split. A few years ago, I worked on creating a clustering system called cohorts. And cohorts clustered people based on their net worth as well as their age. This is a system that gets used by financial service providers like banks and brokerage houses. And if you think about the general population, the vast majority of the general population has a net worth that's not that high. So say $100,000. A large fraction of the population sits down in this region where they just don't have a lot of assets. So we called this group the mass market. Then there's another large group of people between, say, 100,000 and a million. These are called the mass affluent sometimes. Individuals with a net worth over $1 million are millionaires. And there's fairly small numbers of millionaires compared to these other groups. If you just throw things into a cluster analysis, what you find is that you don't get a lot of segments that have millionaires in them. But this group is the one that banks and brokerage houses care most about because that's where the money is. So what we ended up doing was clustering by group. Another issue that comes up with these is the mass market uses different financial products. So you have a lot of checking accounts and certificates of deposit, whereas the millionaires are doing a lot more investing in the stock market and more complicated financial products. So the variables that we had, so how much you do in equities versus bonds, were most relevant out on this end of the spectrum, not as relevant down here. And so we developed 3 different sets of clusters just so that we could have enough clusters identifying different types of millionaires, and then a very different set of clusters defining the types of segments that you get in the mass market. So those are examples of initial splits. Having created the variables, Now you have to choose the variables that you want to use in the cluster analysis. Then you'll have to run a clustering method. We're going to start with k-means. K-means is a good general purpose method, but we're going to study a couple others. We'll talk about hierarchical clustering. The problem with hierarchical clustering is that it doesn't work well with very big data sets. We'll also talk about mixture models, which can handle categorical variables and non-spherical clusters. Having picked a clustering method, the next step is to transform your data. Then we'll find various cluster solutions, profile them, and pick one cluster solution that we think does the best job to solve the business problem. So which variables should you use when you're clustering? So let me state something obvious, but the clusters that come out will depend on the variables that you use in it. So if I use it in the cluster solution, it enters into the objective function, and we're trying to make clusters as similar as possible within on those variables, and the different clusters as different as possible from each other on those attributes. So whatever attributes you choose will be the ones that are used to separate the units so that they're homogeneous on those attributes within a cluster and heterogeneous across clusters. So how do you choose those variables? Well, my view of this is to think about where you need to end up. And so at the end of the day, you need clusters that are going to be actionable. So maybe it's useful and actionable for me to separate out head colds from chest colds. If that's the case, let's find attributes that will allow me to separate a head cold from a chest cold. A heuristic that I commonly use is this. If I had groups that were high on this variable and other groups that were low on it, what would I do with that? And if I can't think of anything interesting, then that's probably not a good variable. On the other hand, if I can think of specific things that I would do, then it's probably a good variable. So an example that I like to use here is, how would you group species, animal species? So one approach could be doing things like measuring the number of inner ear bones, or does this species have fur or scales? Does this species have lungs or gills? Does this species nurse its young? Are they hatched or are they born? So these sorts of attributes are very interesting if you want to be able to study evolutionary biology. And if you use those attributes, you're going to end up putting, for example, mice and whales in the same group of mammals. Likewise, you might put a giant ostrich in the same group as a tiny hummingbird, because they're both birds. But what if you're a zookeeper and you're trying to design habitats? So I need to put different species together into a habitat that makes sense. Well, if that's your objective, if that's what's actionable, you wouldn't want to put mice and whales in the same habitat. Other attributes would be much more relevant, such as the need for salt water, the mass of the species, the length. So mice and whales would be very different on those sorts of attributes. So clearly the meaning of what is interesting is highly subjective and requires a lot of domain knowledge. You need to know something about whatever field you're operating in order to choose good variables. So we'll talk a lot more about step 4 later, which was around which algorithm do you use. Before you run the algorithm, though, you'll probably want to standardize your data. So most clustering methods are very sensitive to the way you scale the data. So as an example, let's say I had x1 and x2, and maybe x1 is measured in kilograms, and x1 is measured in meters. And maybe I have nice round clusters. Now what would happen if I had chosen to express x1, say, in centimeters, and I'm going to keep x2 in kilograms? Well, what would happen is that all of these differences in the x1 direction are going to get exaggerated. So instead of having a nice round cluster, I'm going to have a horribly elongated cluster that's 100 times the width that I had before, and another elongated one up here. So notice something as simple as changing the units on one of your variables could have a profound effect on the shapes of those clusters. So the first rule of standardization is if all of your variables have commensurate units, so all of my variables have been measured in centimeters, or all of my variables have been measured on 7-point Likert scales, then there's usually no need to standardize them. And in fact, standardization can actually distort the data. So one popular way of standardizing is to use z-scores, where I take x minus the mean, divide by the standard deviation. So let's say I have two variables, and maybe I have a cluster that looks like this, and I have another cluster that looks like this. So what I'd like for you to notice is there's low variance in the x1 direction, whereas there's comparatively high variance in the x2 direction. So if I were to cluster this without any standardization, I would definitely end up with these two clusters. But what happens when I standardize? Well, I'm going to take z1 will be x1 minus the mean divided by its standard deviation. z2, of course, is the same thing, replacing 1 by 2. Now what's going to happen is sigma 2 is large. So sigma 2 squared is the variance in this direction. So I divide by big numbers, and the relative variation in the z2 direction will be much smaller. Likewise, the standard deviation of x1 is very small, so I divide by a small number. I'm going to have a lot more variance in the z1 direction. So if I standardize the data first and cluster on the z's, I'm going to pay a lot more attention to differences in this direction and pay much less attention to differences in the x2 direction. So if I have some variable like x1 that's just naturally low variance, I end up inflating the variance of that by standardizing and paying more attention to it than I probably should. So if all your units are commensurate, then you probably don't want to standardize. Now there are exceptions to that. For example, let's say I've got skeletons and I've measured the diameter of the skull. I've also measured the length and the width and the girth of the skeleton. There will naturally be more variation in length than there will in the diameter of a skull. And so I might want to standardize in that case, because otherwise I would just ignore the skull diameter when I do my clusters. What happens if you have incommensurate units? So maybe I've got one variable measured in kilograms, another variable measured in inches, another variable measured in degrees Kelvin, and who knows what else. What do I do then? Well, there are two main approaches to standardizing. I call these the symmetrize and standardize approach and the quantile approach. So the symmetrize and standardize approach says this: if you have skewed distributions, take logs first. So if I have a distribution of some x that looks like this, what typically happens is you spend a lot of your clusters explaining the tail, and that's probably not what you want to do. So you may have some clusters that get divided up like this, and you end up with one giant cluster. Say 70% of your cases are in one cluster. So whenever you have a situation where one cluster is very large, it's probably due to having some very skewed variables. So when I take the log of this, the distribution will often look fairly normal, and we like clustering normal variables. So often that gives us a very interpretable solution. So having taken logs of any variables that had these long tails, the next step is to compute z-scores for all the variables. Now remember what happens with the z-score. If this is measured in centimeters, and then the mean will also be measured in centimeters, the standard deviation will get measured in centimeters, so the units cross out. So z-scores are said to be unitless measures. Another thing that's said of z-scores is that the unit of measure is the standard deviation. So a difference of one z-score means one standard deviation. So z-scores are a completely reasonable way to standardize after you've symmetrized the distributions. Another approach that works quite well in practice is what I call the quantile approach. With the quantile approach, you're first going to find quantiles, so say deciles, and then use the quantile number in the clustering. So let's go back to my picture. What would be the deciles of this right skew distribution? Well, let's just write decile x. The distribution of deciles will look like this. So I'm going to have 10% in the lowest decile, 10% in the next decile, all the way up through 10% in the top decile. So if you use decile scaling, you transform to a uniform distribution. If you use the log transformation, you tend to get a normal distribution. Now, something that I find kind of interesting about the difference between these two distributions is that you're forcing more mass in the tails if you use the decile transformation versus with a normal distribution. There's just not a lot of mass in these tails. So it's like you're inflating the differences when you use the decile scaling. And so what I find is that often you come up with similar conclusions, whether I do deciles or logs, but things are often a little bit clearer using the decile scaling. Another form of pre-processing is finding multivariate transformations. So the most common of these is to average certain variables. We're going to go through this theater attitude data set in a subsequent video. And there were actually 10 questions that all measured respondents' attitude towards theater. Is it fun versus not fun? Is it stimulating versus not stimulating? And it turned out there were high correlations between them. So if I think theater is fun, I also tend to think it's stimulating. If I don't think it's fun, then I don't think it's stimulating. So there's a lot of multicollinearity between them. If I included those 10 variables in the analysis, the effect would be to weight up the person's attitude. So it's like each one of those questions is measuring my attitude towards theater. That gets counted 10 times, whereas some other attributes that you may want to include in the cluster analysis wouldn't get counted as many times because you just didn't have as many questions on that. So you're better off understanding what these underlying dimensions are and using those in the analysis rather than just dumping variables in there without really understanding the multicollinearity. We're going to talk a lot about these issues in the last week of class when we cover numerical latent variables and factor analysis. Okay, so having chosen our variables, chosen the method we're going to use, and done various pre-processing on the variables, the next step is to go find different cluster solutions. So I would recommend starting with some ballpark number of clusters that you can support doing whatever you're doing. So if you're a business and you've never had segments before, maybe you can't handle supporting 30 segments. So start small, go 3 to 5. If I'm a doctor, maybe I don't want to have 10 types of treatments for different types of colds. Maybe I just want 2 or 3. That's all I'm going to be able to get my doctors to do. So don't go look for the 10 cluster solution. Keep it small. Now, once you've established this ballpark number of clusters, go off and find different cluster solutions with those numbers of clusters. So I could find the 3-cluster solution with k-means, then also the three cluster Gaussian mixture and the 3-cluster Ward's method. Then I could do the same for 4 and 5 and compare them. So how do I compare them? In my view, the ultimate goal of a cluster solution is to describe the data in a way that's actionable. And so you need to think about, if I had this 3-cluster solution versus this 4-cluster solution, what does the 4-cluster solution do for me that the 3-cluster solution didn't? Is it more actionable? Are there other things that I can do? Can I justify having that 4th cluster? To me, that's the most important criterion. We'll discuss various fit statistics later on that you can also use to inform your decision. But in my view, the top criteria is this one, which method allows for the best actions. I should also point out that this is sometimes an iterative process. So it's not uncommon for me to try a cluster solution and some variable that I had in there turns out to dominate the cluster solutions, and I don't want that. I want the other variables to also have a say in this. In that case, I might weight down that variable that's dominating everything, or I might add some other variables that would be interesting to have enter into the cluster solution.